complex number z, this would be equal to a plus ib, okay, where a and b, they are both real numbers. Okay, so a, b, they are real numbers, and I, it is equal to the square root of -1. So we start mathematics with discussing the issue that the square root of negative numbers is not defined, but then we came up with a solution or with a notation which we identified this one as I, which was equal to the square root of -1. So the initial need for such a number comes from the idea that for any polynomial of nth order we need n solutions. But these n solutions, they are not always in the real number domain. Okay, so they are not numbers that we can plot them or we can find them in the real number domain. So let's see an example. So we can have a polynomial of z squared minus 4z plus 5. This is equal to 0. So here we have a polynomial of second order in z. So we should get two solutions. We should get z1 equal to something and z2 equal to a different value. Now this is what we are going after, and now we can find the z as z12. This is equal to minus b plus minus b squared minus 4ac, so we get 16 minus 20 divided by 2a. So this is expression minus b plus minus b squared minus 4ac over 2a. And then we end up, sorry, this 2a, a is 1, so this can be divided by 2. So this would be equal to 2 plus minus the square root of -4, square root of -4 over 2, and this would be equal to plus minus the square root of -1 times the square root of 4 divided by 2. Square root of 4 is equal to 2, so these two numbers can cancel each other, and this would be 2 plus minus I, okay? So this would be the solution of this polynomial. And then we can say that this is equal to 2 plus I, and the other root is 2 minus I. So these two numbers, they are complex numbers, and an important question is where can we find these two numbers in the graph? Okay, how do we plot it? So these two numbers we can consider as if this is a real part of z1, and real part of z1 is equal to 2. And we have also imaginary part of z1, this is equal to 1. Okay, and then the real part of z2 is equal to 2 again, and the imaginary part of z2, this is equal to -1. So this is how these numbers are denoted, and for this we have developed a graphical way how to represent these numbers. Here we write the real part of z of the complex numbers, and here we write the imaginary part of these numbers. So now the real part of z1 it's equal to 2. So we write here 1, this is 2, and the imaginary part of z1 it is I. Now I, this is I, okay? So because the imaginary parts we denote them in the vertical coordinate system. So it looks like z1 is right here, okay? And this is z1, z2, imaginary part of z2 is equal to -1. So this denotes the minus I, and then we're talking about this point, which is going to be z2. Now, so it looks like this is called an Argan diagram. I often forget this one. This is not very essential, but this is called the Argan diagram. So we're happy so far because we know. So we obtained two different solutions for the polynomial, as we should have done. If the square root of negative numbers was not defined, we would find no solution at all. And by the way, if we try to plot this graph, z squared minus 4z, we can write this one. This is z minus 2 all squared plus 1. Is this correct? Because this is equal to z squared minus 4z plus, plus 1. Okay, this is equal. Okay, so this is the polynomial. And z minus 2, whatever z is, this will always be a positive number. Okay, with the smallest possible, and this would be 0 only when z is equal to 2. So this is 1, this is 2. So initially we can have this graph, but then we can lift this whole graph 1 unit higher. So this is the drawing of the graph z squared minus 4z plus 5. So we see that this one, it never intersects with the x-axis. I mean, the intersection with the x-axis would traditionally give the roots of a polynomial, at least in this case for a quadratic polynomial. Okay, so now the manipulation of complex numbers, it is similar to vectors. Okay, so operations such as addition, subtraction, it is similar to vectors in the way that it's a vector with two components, and we add the first ones with the first ones and the second ones with the second ones. And examples could be as follows: z1 is equal to 2 minus I, z2 is 3 plus 4i, and z3 can be equal to 4 minus 5i. So here we have three complex numbers, and then we can define z1 plus z2. This would be equal to 5, 2 minus I, plus 3 plus 4i, plus 3 plus 4i. And this is equal to 5 plus 3i. So this is the summation of between these two complex numbers. At the same time, we can also assume that z1 is a pair of numbers which looks like this: 2 minus 1 plus, using a vector notation. Okay, we use 3, 4. 3, 4. So this will be equal to 3, 2, 5, 3 here. Okay. So it is good if we can make use a little more, if we use a better graph. So allow me for a moment. Let's erase. Oh no, let me do it here actually. We can see this part. Yes, we do. Okay. So the first number is 2 minus I. So this is 2 minus I. It's minus 1. It's here. So we have this number. The second number is 3 plus 4i. This is 3. 4i, 1, 2, 3, 4. So this is Z2. This is Z1. Z3 is 4 minus 5i. This is 4 here. 1, 2, 3, 4, 5. This is 4. So this is Z3. Okay. So we added. What did we get for Z1 plus Z2? Z1 plus Z2, we got 5, 3. So we got this one. This is 5 and 3. It's 1, 2, 3, 4. So apparently we ended up into getting. This is Z1 plus Z2. So it's, or we can assume this one as if this is Z1, this is Z2, and these are added like vectors, right? Because Z1 is like it's carried this way, and we get this one. So this is Z1 plus Z2. So it looks like the addition of complex numbers in the Argan diagram, they look good, they are elegant, okay? But the beauty about the complex numbers, this is not shown only in the addition and subtraction. We can see it a lot in the multiplication of complex numbers too. And the multiplication of the complex numbers is also defined, and it can be expressed in at least two different ways. the way that we multiply the complex numbers. Let's see what we have, some other notes. Okay, so for complex numbers, we can define modulus and the argument. So modulus and argument is defined as, for example, if we have modulus is defined as, we denote this one like this, and this is equal to the square root of x squared plus y squared. So this is somewhat equivalent to the magnitude of a vector. And then, and here, this one is in fact defined in a more general term like this. The magnitude of z, and before we do this, let's remember once again how we defined the length or the norm of a vector. So we said that the magnitude of a vector v, okay, this was equal to the square root of v transpose times v, right? So this is what we have used so far. Now here in the complex numbers, the notation that we use is the following. This is z complex conjugate times z. Okay, so this is what we do. But in fact, we have not defined the complex conjugate yet, so let's do it here. So z1 complex conjugate, we denote this with a sign here. This is going to be, we just change the sign of the complex number. It's going to be 2 plus I. Okay, so then if we are to show z1, z2, and z3 on the complex number plane, so if this is z1, z1 complex conjugate is going to be at this point. Okay, so this is z1 complex conjugate. z2 complex conjugate, this is equal to 3 minus 4i. So 3 minus 4i, so z2 is here, it will immediately be projected 1, 2, 3, 4, right here. So this is z2 complex conjugate, and you can see that in fact they are somewhat the reflection with respect to the x-axis. And then no need to do this. Z3 complex conjugate is going to be 4 plus 5i. And 4 plus 5i, we will find it somewhere here. Because this will be the 5, this is the 4, and this will be the kind of the reflection with respect to the x-axis of the Z3. So this is called, let's define here actually, this or let's define here complex conjugate. Complex conjugate. Now, why do we need this here is that the definition of complex conjugate, it has some similarity when we try to find the magnitude of a vector. So let's assume that we have a vector z1, or let's assume that vector v is a vector defined by 2 minus 1. Okay. What is 2 minus 1? Sorry, this is 2 minus 1. This is the vector-like representation of this complex number. And then what is the magnitude of this vector v? Sorry. Okay, we can denote this one here, and the magnitude would be equal to v transpose times v. V transpose, it is 2 minus 1, and here we have 2 minus 1. When we do this multiplication, what will be the dimension of the multiplication of these two vectors? This is 1 by 2, this is 2 by 1. So if you multiply a matrix or vector which is 1 by 2 with one which is 2 by 1,
we got a scalar?
Say it again, it's a scalar, right?
We've got a scalar?
Yes,
that's the square root of 5.
Thanks for the confirmation. This is the square root of 5. That is true. So apparently, and then we can also see it here. So 2 minus 1 is going to be the length of this vector. And using the Pythagorean theorem, we find that it is square root of 5. But what we care for the moment is to remind ourselves on the intuitive similarities between the complex numbers and vectors. So now let's find what is that complex conjugate. So let's multiply this number with this number, because this is the Z complex conjugate. So let's do here. We will have here the square root of 2 plus I times a number which is 2 minus I. And this is equal to, so this is the square root of, what is 2 plus I times 2 minus I? This is similar to the multiplication A plus B times A minus B. What is this?
A squared minus B squared.
A squared minus B squared. That is true. Now, in this case, let's do here 2 plus I. 2 plus I times 2 minus I. This would be equal to A squared, which is 4, minus I squared, right? Minus I squared. Now, what is I squared?
Minus 1.
Minus 1, so this is
Plus
going to be, this will be 4 minus 1. You are right, plus 1 is 5. So it looks like a complex conjugate times itself. So let's write it like this here. This is equal to square root of 5. Okay. So apparently the modulus of a complex number, this is how it is defined. And what we want to see here is that the modulus is also equal to Z complex conjugate times Z. Now the argument, this other element here, this is tangent inverse of y divided by x, okay? Or, as we call this one, this is also called the arctangent, okay, the tangent inverse. So this tangent inverse, if we consider the argument for Z1, so here we have argument of Z1, this will be equal to the arctangent of y. What is y? What is y here? Because we are discussing about Z1, this number.
Minus 1.
Minus 1, that is true. This is minus 1, and we divide by x, which is 2. So this will be, we have to find, this is the arctangent of this value. So we are given the tangent, and we want to find the angle. So we are looking for this angle here, which, with respect to the x-axis, it looks like it's going to be a negative number. And what is interesting or very useful here, it's used to remember, is that in the Argan plane, the angles, the complete angle here, it is 360 degree, okay? So it is 360 degree, and you can denote these angles anything from 0 to 360, okay? Or, at the same time, this is equivalent to saying the angles from minus 180 to plus 180. It is the same thing, okay? Now, we like to use the pi notation. So this angle can be from 0 to 2 pi, or from minus pi to plus pi, okay? So what's wrong with me? It's plus pi. So it looks like the whole 360 degrees, they can be denoted from this point, and then from minus pi to plus pi, okay? So this is the 2 pi, the complete angle. Then, and it looks like the argument for Z1 is going to be a negative number. If we denote, if we use this notation, and this is unacceptable, often you might see engineering textbooks using this notation from minus pi to pi, or from minus 180 to plus 180. Okay, so it looks like this is what will be the arctangent. We have to figure out what is this. So in principle, we have the equation that we have written here. It is equivalent to saying the following. We have a tangent theta, which is equal to minus 1 over 2. Okay, and the question here is theta is equal to 1. So we are after the number. Okay, and now regarding the plane, here we have the Argan, how do we call this one, construct, and here it is almost obvious that this we can call also the phase plane, planiphasor, phase plane, okay. Why do we call this one phase plane is that often the square root of -1, or wherever we see this I, this is somewhat equivalent to having a phase, okay? It is not an amplitude, it is not something which increases exponentially, because we can have here 2 to the power n. So when n is a large number, we can have 2 to the power 10, we know that this is an increasing function. But if we have I to the power n, what is I to the power n? This is an oscillatory function, but this one we will understand a little later, okay? So real numbers, they can exponentially increase or decrease. Complex numbers, they are oscillatory, okay? Since they have an oscillatory behavior, we can also call this plane as a phase plane. And this phase plane, we can divide this one into 4 quadrants, okay? 4 quadrants. The first one would be this, where x and y are larger than 0. This would be the second quadrant, okay, where x is negative, y is positive. This would be our third quadrant, where both x and y, they are smaller than 0, okay. Here we go to the fourth quadrant, where x is positive, y is negative. So we can quantize the phase space into 4 quadrants. We can quantize it also in different ways. So this phase plane, what we can do is that, so as we said, maybe I can show it like this. So the phase plane, the first level quantization could be, we can quantize it in 2 levels, which would be what? Anything which is above here can be the first part, and any angle in this domain can be the second part, which means that, so what you can say is the following. You might cluster, you might classify, so let me use these keywords. We may cluster or classify or categorize complex numbers, we can separate them in 2 different domains. Whether a complex number is above the x-axis or whether a complex number is below an x-axis. So if we see this example, we can say that Z1 is in the second part. Okay, so let's assume that if we quantize this like 1 and 2, okay, where 1 is covering this whole thing, then we can say that in 1 we have Z1 complex conjugate, we have Z2, we have also Z3 complex conjugate, because Z3 is here. Or this was one way. Another way, it was to separate, as we said over there, to separate this into 4 quadrants, which would be 1, 2, 3, and 4. This is possible. Another way, we can quantize this a little more by also separating these phase plane a little more, which would mean that we can have 1, 2, 3, 4, 5, 6, 7, and 8. Okay, what do we mean with this? So we sometimes, for some application, for some very useful application, we may be interested into figuring out where a representative or a quantity which is represented by a complex number, where does it fall on the phase plane? Okay, so we may be interested to check whether a specific complex number falls from the angle 0 to 45 or from 45 to 90, and we want to check the similarities between 2 different data sets. This is one of the most important areas where this can find a use. So as you can see, as we said, the phase plane, we can quantize it in two levels, in 4. 4 is the more traditional one. In 8, And we can also quantize it a little further into 16 different parts. So which means that we can divide the angle of 45 once again. Okay, so it is really important trying to think in terms of the angle in the phase plane. Okay, so let's see. I think we did an example here regarding the. So let's give another. Let's write down something here. So here we have the arctangent of -1/2. Let's use a calculator and try to see what is this angle to get a precise representation of this. You can also use your calculators, and it's good to experiment with these. I don't know if my cell phone has a. Wait a second. I can write here super scientific. I don't have a tangent inverse. I should have. Or I cannot find it. I found it. Okay. So here we have that we can enter arctangent of -1 divided by 2. -1 divided by 2. And it looks like we have an angle of -26.56. So here, the angle theta is equal to -26.56 degrees. Okay. So this is the angle, or this is the argument of Z1. Now, this is in degrees, and we may be interested into determining what this angle is in radians. Okay, and we know that 180 degrees, this is equal to pi. And this pi, these are radians. And so this is the case, and then -26.56, this is x, so this is the unknown value. So how many radians is this? To convert this into radians, we do the following. The x, this will be equal to -26.56 times 3.14 divided by 180. Okay, so this is how many radians this is going to be. So then we have here -25.56
-0.46.
3.14 divided by 180. I get an error in what was it?
-0.46 radians.
Okay, -0.46 radians. Okay, that's good. Now, here we are. So we got the solution, or here we had an example of how the argument can be found. Now we move to a more beautiful part regarding the complex numbers, which is the multiplication. The multiplication, it is not that difficult. It is the same way as we're multiplying two parentheses, okay? So the multiplication is going to be, it's best if let's multiply here Z1 and Z2. Z1 times Z2, this will be equal to 2 minus I, and of course we're reading this here, 3 plus 4I times 3 plus 4I. So this will be equal to 6 plus 8I minus 3I minus 4I squared. Okay, so all we did, we are multiplying two terms by two terms, so we get 4 different combinations, and then of course this is how as much as we can get. Then this is the real part. This is 6 plus 5I minus 4 times -1, because I squared is -1, and then here we obtain this is plus 4, this is equal to 10 plus 5I. Okay, so this is what we get here for the multiplication. And we have also some important relationship, which is the following. The modulus, or the magnitude of Z1 times Z2, this is equal to the magnitude of Z1 times the magnitude of Z2. Okay, this is a property of the complex numbers. It's a very useful one. At the same time, we have the argument of Z1 times Z2 is equal to the argument of Z1 plus argument of Z2. Okay, so this was addition. Let's take this away. And let's write here the modulus and the argument. So for Z1, we got minus 26.5. Let's write here minus 26.56. The modulus, this was square root of 5. And then Z2, we can try to identify what is the magnitude of Z2. This is modulus magnitude. Magnitude is not the correct word, but since this is, you know very well linear algebra, you can draw the equivalent principle that we are considering. So the magnitude of Z2, this is equal to the complex conjugate of Z2, okay, Z2 complex conjugate, times Z2, and this would be equal, so Z2 complex conjugate is 3 minus 4i. So here we have 3 minus 4i times 3 plus 4i, and this will be equal to, as we say, a minus b squared. So this will be equal to 3 squared, it is 9, minus 4 squared I squared, right? What is 4 squared I squared? This is equal to plus 16, right? Because I squared is minus 1 plus 1, so this is what we get. Then we get the square root of 25, which is equal to 5. So it looks like Z2, the magnitude, it is 5. Now, what is the argument? The argument of Z2, this is equal to arctangent, or tangent inverse, of the y over the x, which is 4 divided by 3. Can you calculate this, what this is? I remember there are some angles like 53 and 47, 37, 53.
Minus
So
53.1.
But it should be plus.
53.1.
Okay, why is it 50? Okay, 53.1. This is 53.1 plus, right? So this is the angle 53.1. Okay, that's good. Now let's check if these properties are true, or let's confirm this statement. So let's erase this part. And meanwhile, I want you to go over your notes and try to try to find, we have done an example a few weeks ago where we had a matrix, which I don't remember exactly, 1 minus 1, 1, 0. So please, and because we also tried to, we found what were we were noticing something that a cubed was equal to I. If you remember such an exercise that we have solved before, please go and find it, because I want to go over it. And meanwhile, let's come back here to the class. So here we have argument of Z2, that's what we get. Then we notice that so this is the general rule. And let's see what is the magnitude of Z1 times Z2. Magnitude of Z1 times Z2, we can distinguish, we can write it like this. This is going to be equal to Z1 times Z2. The magnitude would be equal to the complex conjugate of this 10 minus 5i times 10 plus 5i square root. And this is equal to the square root of 10 squared plus 5 squared. So this will be 10 squared plus 5 squared. So this will be the square root of 125. Square root of 125. Square root of 125, it is
11.1.
so square root of 125, this is equal to the square root of 25 times the square root of 5. The square root of 25, it is 5 times the square root of 5. So what is important for us is that we notice that if we multiply z1 and z2, we get another number whose magnitude or whose modulus is 5 times the square root of 5. Okay, so this is what we wanted to confirm, so this was an interesting and useful property, as we'll see very soon. Now, what is the argument? We know the argument, well, we found both, right? Now let's find the argument of z1 times z2. What is it? This is going to be equal to the tangent inverse of the y over x, right? So this will be tangent inverse. What is y here? 5 over 10. Because this is the number. And 5 over 10, can you find what is the argument? Using a calculator.
26.5.
Yes.
Say it again.
26.5.
26.5. Now, what remains for us is to check whether the summation here is really 26.5, is it?
Approximately, yes.
Okay, so approximately yes. So it looks like we confirm that if we multiply two complex numbers, the angle that it creates with respect to the x-axis will be the summation of the two angles of the respective complex numbers, and the magnitude or the modulus will be the product of these two values. Okay, so this is an important property. And now I want to go over to have a look at these principles that I call rotation. Before a while, we said that real numbers, they exponentially increase too fast if we take any number to the power n. So let's have a look of what happens in this Argan plane. In this Argan plane, let's pick a number which is 3 plus 2i. So let's pick this one, z minus i. 2 minus i. This is 1, this is 2, and this is minus 1. This is z1, and this one is shown right here. Okay. So this is z1. Now let's multiply z1 by I. So what is z1 times I? This is equal to 2 minus I times I. What is this? This is 2i minus I squared, right? Which is 2i plus 1. So what is the real part here? The real part is 1. So then I times z is a number which is shown somewhere here. So this number, this is I times z1, okay? Let's multiply by I again. So let's multiply this number by I. So we get z1 times I squared. If we multiply this by I, we get 2i squared plus I, right? 2i squared plus I. And then 2i squared, it's minus 2 plus I. So what is the real part of this number? The real part is minus 2. So here we get minus 1, minus 2. And the imaginary part is I. So this is equal to I squared z1. And now let's find what is z1 times I cubed. z1 times I cubed, let's multiply this number by another I, okay, which is minus 2I plus I squared, which is equal to minus 2I minus 1, because I squared is minus 1. So what is the real part? It's minus 1. The complex part is minus 2. So let's have here minus 2. So this number, this is I cubed times z, okay? Now, let's multiply again z1 by I to the power 4. z1 times I to the power 4. This is equal to, let's multiply this number by I. We get minus 2 I squared minus I. Okay? Minus 2I squared, it is
I.
2 minus I, that's correct, which is equal to z1. So, by multiplying this number here by I, we get to this point where we started, which means that this is equal to I to the power 4 times z1. And now, what is something that we can notice here is that because of the symmetry, and we can also calculate the angles, here, the angles between these are all 90 degrees, okay? So, it looks like if we multiply a complex number by I, what we are really doing, we are rotating it by 90 degrees, okay? I believe, is it clear?
Yes.
Yes.
Okay, so it looks like we say that z, any complex number z times I, this is equivalent to a rotation. To a rotation by 90 degrees, or you can say rotation by an angle of pi over 2. Okay, now, so apparently this is what we obtained here. At the same time, we can also multiply z with 1 minus 1, right? If we multiply z1 minus 1, we would get, if we start with z1, if we multiply by minus 1, we'll get immediately this. If we multiply by minus 1 again, we'll come back here. Okay. So multiply by minus 1, this is rotating by 180. So z times minus 1, this is equivalent to a rotation by 180 degrees. Okay, so this is what this multiplication gives for us. So I believe we remember these examples, so let's take them away for a moment. Okay. So we talked about the complex conjugate and many more. And actually, complex conjugates, we can write a few properties. In fact, for the moment here, considering the complex numbers, so it looks like the language that we try to use in the last few minutes, we are using the language of rotation. Where have we seen the concept of rotation so far? So, if we multiply a matrix with a vector, what happens to the vector? Will the vector preserve its direction? So if we multiply a matrix by a vector, what happens to x0? Will the x0 stay in the same direction?
It will rotate.
It will not be. So let's assume for a moment, or let's write it like this, b. So we know that we multiply vector x0 with b, and most probably there is an angle different from 0 between b and x0. When is the case? When, so it looks like multiplying by complex number, it is a rotation. So let's write it here for a moment. So this rotation, it looks like we have not concluded completely, but this rotation, this is represented somehow by these complex numbers. Let me write it like this, okay? At the same time, a rotation is also defined by multiplying by a matrix. You agree on this one too, right? But now, we also know that for some specific vectors, the vector is not rotated. When is this the case? Is it possible to find a vector which is not rotated at all?
The eigenvectors.
Exactly. That's true. So there are some vectors, and this is why we believe that it is very important to try to relate together the concepts of rotation, the concept of changing the basis, and also the similarity or equivalence with the complex numbers, because it helps you build up a very solid understanding of space. And here it looks like, yes, that's true. In the most general sense, it represents a rotation. It represents also a change in the length, in the magnitude. The same way like the multiplication of two complex numbers did, right? So we multiply Z1 and Z2, what did we find out? We found out that the modulus of the result is equal to the product of these two. But now let's see for a moment. What is I times Z1? What is the modulus here? This would be equal to the modulus of I times the modulus of Z1. What is the modulus of I? So what is the modulus of I? This is equal to the square root of complex conjugate of I. What is complex conjugate of I? It is minus I. Okay, so we change the sign of the complex part. Times I. So what we are writing here, we are writing this. Z complex conjugate times Z square root. Again. So what is minus I times I? Minus I squared. Okay, square root. I squared is minus 1. Minus 1 is 1. So square root of 1. This means that this is 1 times square root of 5. So it looks like if we multiply a complex number by I, we don't change the magnitude or the modulus. Why? Because I, it has a modulus of 1. But it brings a rotation by pi over 2. Okay? Now, we multiply by I, and we change it by pi over 2. We multiply Z1 with Z2. And what happened to Z1 when it was multiplied by Z2? This angle, it was modified from minus 26 plus 53, it became 26, okay? So it looks like we are rotating the complex numbers in the Argan plane whenever we are multiplying two complex numbers. I believe, is this obvious? So it looks like we are seeing a couple of examples where here the angles were added together. Here, for example, let's do this one actually. So what is the argument of I Z1? The argument of Z1 is equal to the argument of I. What is the argument of I? What is the angle in the complex plane if we are to show I? So this is I. What is the angle here?
90 degrees.
That's correct. This is 90. So we say here this argument of IZ, this is equal to 90 plus the angle of Z1, which is minus 26. Minus 26.56.6. And this would be equal to something like, what is this? 864.63.4 degree plus, okay? So this is what is happening here. And it is good to have a look for a moment to discuss the following. What is the argument of I? You said it's 90, that's true. What is the argument of minus 1? What is the argument of minus 1?
180.
That is true.
From my or
I don't know whether it's minus 180 or plus 180. We pick one. We pick 180, okay? This is the argument of minus I. What is the argument of, minus 1. This is the argument of minus 1 because this is the number of minus 1. What is the argument of minus I?
270.
That is true. So this
Or
is
minus 90.
It can also be minus 90. That is true. So maybe it's better to consider minus 90 or to consider this one minus pi over 2. Okay. We can also ask the following question: what is the argument of minus 1 plus I? What is the argument here? Now, minus 1 is here, plus I is here, so it looks like we're looking for this point. Psychaconic.
Non dietros de pés,
Well,
geometria de pés.
here to the best. That's correct. 135. This is the argument of this angle. At the same time, what is the argument of the... Sorry. Let's take this away. We don't need this for a moment. What is the argument of 1 minus I? 1 is here, minus I is here, so we're talking about this angle. What is the argument of 1 minus I?
Minus 35.
Minus,
Or we're gonna write it in a big dude.
minus 45. Or minus pi over 4. Because this is half of this angle. Okay, so now it looks like if the argument of I, 1 minus I, is minus 45, that means that if we multiply 1 minus I with Z1, what will happen to Z1? The answer, it will go from minus 26.56 minus 45 degrees. So most probably, so we are discussing multiplying Z1 with this number here. Then, where is minus 26? Minus 26 is, this is 45, 26 probably is an angle around here, okay? Maybe this is not precise. So this is minus 26 approximately, which is Z1, right? We multiply with this number, so we go minus 45 again, so we go another minus 45, so we're going to go somewhere here, okay? So plus 45, plus, so this will be, we're going to find that Z number along this, with respect to this angle, right? The only thing, where are we going to find it? We are going to find it, so, can you help me? So where is this point, or what is the magnitude of multiplying Z1, so let me write here, Z1, let's multiply it with 1 minus I. What we will do, so we found the angle, right? Now we need to find the magnitude. What is the magnitude of 1 minus I? What is the magnitude here? One squared plus 1 squared, square root of 2. And the magnitude of Z1, it is square root of 5. So these two will be a number which has a magnitude of square root of 10. So what we will need to do is, along this direction, we are going to count a length square root of 10. So we draw a circle with a radius of square root of 10, and we might end up somewhere here, okay? Because we know the angle, we know the magnitude, we can find it. Now, we did this one a little earlier because it is intuitive, but we are going to give we're going to see once again how we multiply two complex numbers in terms of using only the modulus and the argument. Because we know that, in fact, let's assume that we have a number which is Z4, which is equal to Z1 times Z2. So to find the point Z4, what do we need? Well, we need an angle. Well, we also need these. To find Z4, we need to know X4 and Y4, right? But at the same time, we need also a magnitude or a radius and an angle theta. Either this or this. They both are explicit of each other. So we can either find X4 and Y4 or the angle. How do we find the angle? We just add up the angle which corresponds to Z1 and the angle which corresponds to Z2. We find this. How do we find this radius or the magnitude? We multiply the moduluses of the two respective values. Okay, and then just a couple of examples very fast. So what is the magnitude of 3 minus 4i? This is equal to the square root of 3 squared plus 4 squared, okay? Or 7 minus 2i, what is the magnitude here? It's going to be 7 squared plus 2 squared. And also 5 minus 6i plus 6i. This is going to be the square root of 5 squared plus 6 squared. Okay, so this is how we always get it. Now, complex conjugates, we have some relationships here, which we're going to write them very soon. This was just to argue that the multiplication with I brings a rotation by pi over 2. And then, let's see, let's cover these beautiful properties, which are the following. Z complex conjugate is equal to what? Is equal to Z again, okay? Because Z1, it is equal to 2 minus I. Z1 complex conjugate is equal to 2 plus I, because what the complex conjugate does, it just changes the sign of the imaginary part. So Z1 complex conjugate again, this becomes again 2 minus I. So this means that this is equal to Z1. This is the first property. The second property is Z plus Z complex conjugate. What is it? This is 2 times the real part of Z, okay? Because if we add here Z as Z1 plus Z1 complex conjugate, this is 2 minus I plus 2 plus I. So this is, the i's cancel out, we get just 4. And this 4, it is 2 times the real part of Z1. So let's not forget that the real part of Z1 is 2, and the imaginary part of Z1 is equal to what? What is the imaginary part of Z1?
-1.
That is correct, -1. What is the imaginary part of Z3?
-5.
That is correct, okay. So this is Z plus Z complex conjugate is equal to 2 times the real part of Z. And then we have also that Z minus Z complex conjugate, this is equal to 2 times I times the imaginary part of Z. Okay, if we have any doubt, we can check this. For example, we can, I think this was clear, but wait a second. So this Z minus, so here we have Z1 minus Z1 complex conjugate. This is equal to 2 minus I, 2 minus I, minus 2 minus I, minus 2 minus I, and this is equal to 2 minus 2, it is 0, but minus I, this is minus 2I. Okay, so this is what we obtained here. And then another property is the following. Z divided by Z complex conjugate. Now, what could be the answer? I want to ask you regarding this. These are just some short warm-up exercises, so let me erase this here. And let's think for a moment that we have, let's assume we have Z4 is equal to Z1 divided by Z1 complex conjugate, sorry, that's Z1 complex conjugate. In fact, we have not defined the division yet. This is not maybe the best point because the division is not defined yet, but we can use a couple of arguments that the magnitude of Z4 is going to be equal to the magnitude of Z1 divided by the magnitude of Z1 complex conjugate, in fact, in this case. So let's have a look for the moment. This should have kind of a magnitude equal to 1, okay? And the angle, the ratio here Think about this one. What can be argument of Z1 plus the argument of Z1 complex conjugate? Now, think about this. Let's give the definition, and everything will become clear. We're not expecting to derive them ourselves, but here, this will be equal to the real part, of course, plus I times imaginary part, okay? But what is the real part? The real part here, it is x squared minus y squared over x squared plus y squared. This is the real part, plus I times 2xy over x squared plus y squared. So these are some useful properties. Now the first three ones are intuitive. We know these. The fourth one is a little difficult because we have not defined division by a complex number. But let me, in order to draw some equivalence, what did we do in linear algebra so far? We used to have the multiplication of a matrix A with a matrix B, right? This was good. But did we ever do this? Could we divide B divided by A?
No.
That's true. This is not defined. So we cannot divide a matrix with another matrix, okay? This is not defined. Similarly, the division by a complex number, it is simply not defined, okay? So here we see another equivalence between the matrices and complex numbers, because division, it is not defined, but assuming that we have Z1, which is equal to x1 plus I y1, and Z2, which is equal to x2 plus I y2, okay, so this can be any two numbers, then the division Z1 divided by Z2, Z1 divided by Z2, it's equal to x1 plus I y1 divided by x2 plus I y2. What we can do here is that we can multiply this expression by 1. How can we multiply this expression by 1? We can multiply by the complex conjugate of the denominator. So let's multiply here x2 minus I y2, and here x2 minus I y2. Okay, so this we can do this easily, and we know that for any number, so let me write this fast, z, which is equal to a plus ib. What is z times z complex conjugate? This is always a squared plus b squared. Okay, you can check this. We did this quite a few times because we noticed that the magnitude was always equal to the square root of these numbers. So you can also derive this again, but then here we would have the following. We have here x2 squared plus y2 squared. This is what we get from the multiplication of this term here at the bottom. And for the numerators, if we multiply these terms, we get the following numbers. We have x1, x2, right? This is traditional. We should get 4 terms, so it should be straightforward. x1, x4, then plus y1, y2, plus y1, y2. Why is this? Because we're going to multiply these numbers, okay? And then this is minus I squared, which becomes plus whatever the rest is. And then we have plus I. So this is equal to plus I. Let me erase. Now this part was for demonstrative reasons. Let's erase this. This was...
Professor, це x квадрати. x квадрат.
Okay, should be x2. This is x2, sorry. This is x2 plus I. That was a mistake. So here we have plus I times x2 y1 minus x1 y2. Okay. So, and then what we can do is that the final result, it will be equal to So the division between any two complex numbers is equal to x1, x2, plus y1, y2 divided by x2 squared plus y2 squared plus I times x2, y1 minus x1, y2 divided by x2 squared plus y2 squared. Okay, so this is, in fact, this is how we should do it and we can do an example, but one thing that I don't want to, wait a second. So I believe this part we do remember, so let's take this away. Let's take also this away. We know what we're doing complex numbers. So let's divide what is z1 divided by z2. Okay, so let's do this example here. So let's call this one z4, which is equal to z1 divided by z2, z2, 2 minus I divided by 3 plus 4I. And this is, should be, let's multiply, so this is what we need to find. Let's multiply by the complex conjugate, 3 minus 4I times 3 minus 4I. So this division is not, it's not defined, as we said, but this one is defined. So we should immediately get that in the denominator, what are we going to get in the denominator? We get 3 squared plus 4 squared, okay, which is equal to what?
25.
This is 25, yes. And then we multiply these terms. 2 times 3, 6. 2 times minus 4i, minus 8i. 3 times minus I, minus 3i. Minus, no, this is plus 4i squared. Right? So this is what we get, because minus minus plus, plus 4i squared, then this is equal to 6 minus 4, 2. This is 2 over 25. And what is the rest? Plus, let's write this one plus I, okay, times minus 11 over 25. Okay. So, okay, so this is what we get for Z4. Is it clear?
Yes.
Okay. This was Z1 divided by Z2. This is what we obtained. Okay, so this was. And now we can also say here that the modulus of Z4 is equal to the modulus of Z1 divided by the modulus of Z2. Okay, so this is equivalent when we multiply. When we multiply two complex numbers, the result, it will give a modulus, which is the multiplication of those two numbers. Here we have the division, but at the same time, we have that the argument of Z4 will be equal to the argument of Z1 minus the argument of Z2. Okay, so this is what is going with these. Now, we come to the best part of real numbers that we have seen so far. So not real numbers, of complex numbers that we have discussed so far. This is the polar representation. This is the very intuitive. Many, including myself, find this one very important, which is the following. We have the polar representation. The polar representation of complex numbers, we use a notation which includes angles and the, we need angles and the radius. And the polar representation, the fundamental term that is often seen is the following. E to the power I theta, this is equal to cosine theta plus I sine theta. Okay, sorry, it's not the best pen. So e to the power I theta is equal to cosine theta plus I theta. And at the same time, what we can do to this expression is that we can multiply both sides by r. So we can get the following: r times e to the power I theta. This is equal to r cosine theta plus r sine theta. Now, we can also check the following actually. So we said that what happens if theta is pi over 2? Let's assume theta is equal to pi over 2. What will this expression become? We have that e to the power I to the power pi over 2. This is equal to cosine pi over 2. Cosine pi over 2 plus I sine pi over 2. What is cosine pi over 2?
0.
0.
0. What is sine pi over 2?
1.
1. So this is I. So e to the power I pi over 2, this is equal to I. Okay? So this complex number, which is here, is represented by this number. Okay? Or by this polar representation. And now, it looks like any z number, so this is the beautiful part, any complex number, this can be written as r times e to the power I theta. Okay? And then where r is the magnitude, okay? And then in this case, we can, yes, this is it. Let me think for a moment. So let's try, if we have this notation, so r is the modulus. Let's try to write z1. What is z1 here? z1 can be written using this representation. This will be equal to the, what is the modulus of z1? If we see
Square root of 5.
this is square root of 5 times e to the power I times 26, minus 26. Let me write this one minus 26. We know it's minus 26.56, whatever. Let's leave it like this. Then let's look at Z2. What is Z2? Z2, using the polar representation, what is the magnitude of Z2?
5.
This is 5 times e to the power I, 53, right? So let's write here, this is 53. So this is Z1 and Z2. Now, given these two values, then we can simply find another Z, which is the product. So let's assume Z5 is equal to Z1 times Z2. And then what we need to multiply, we just need to multiply these numbers, right? So we have, and this is easy, square root of 5 times e to the power I minus 26 times 5 times e to the power I 53. Okay? So how is this multiplication done? This is 5 times square root of 5. This is this. 5 times square root of 5 times e to the power I. And here we have 53 minus 26. Because this is how the e to the power A times e to the power B is equal to e to the power A plus B. So we have the property, we follow this property. We apply this here, and we get here 53 minus 26, and as a result, we get here 5 square root of 5 times e to the power I, 53 minus 26, we get 27. Okay, so this is the result, and this one, for many, it's also a lot more intuitive. Okay. So, because this clearly includes the principles that we discussed regarding the rotation. Okay, so this also means that if we have to multiply Z1 with I, what do we get? So, if you are to multiply I times Z1, this is the same way as writing down e to the power I times what? What is the angle here?
19.
Pi over 2, that's
Alpha.
right. That's correct. Z1, this is square root of 5 times e to the power I times 50, minus 26. You know, let me write this 90. You are correct. Let's do this one 90. It's better. So this one, the multiplication of these two numbers will give square root of 5, it's here, times e to the power I, 90 minus 26, we should get 64. Okay? So we get a number Z5, and how can we find the Z5 in this graph? To find the Z5 in this graph, first of all, we need to draw a circle which has a radius of square root of 5. What is square root of 5 approximately? It's 2 point something. What is it more or less?
2.23.
2.23. Okay. So let's go. This is 2.23. It's almost here. So it's almost here, here, and here. So it looks like we can draw a circle, and we know that this number Z5, it is a complex number. It will be found at any point on this circle, okay? Because we know precisely how far it is from the zero. So we can find it on the circle. But at which angle? At angle 64. The angle 64 is here. So this is our complex number. We found it, okay? So this is what is the product of phi times Z1. But wait a second, so okay. Since we already found this actually, wait a second. No, okay, so most probably the 64 is this one, because we have this one. So then the direction should be this. Okay, this is 64 degree approximately. So in fact, most probably the length of this one is 2 point square root of 5. So then this circle would better intersect in here. So my drawing should end up, in fact, right here, because these are all magnitude of Z1. Practic, vectorul ce bămăbiu, în factura de ce un două de zatoiu, pe ce nu că product shumir. If you draw this one with using a software or something, you'll find that really the circle will intersect these four vectors, which we draw them before a few minutes or sections. Okay, so these are what we see here regarding the complex numbers and the operations including multiplication and division. And as we said, the best representation here, it is the polar representation. But now I have to think about this matrix which we came up with few weeks ago. I'm trying to remember. Probably it was 1, 1, 0, 1. No, maybe it was this. You don't remember this magic matrix we came up randomly a few? This was 1 minus 1, 0, 1. Let's try this. Can you try what you get if you write this matrix A? Let me take this away. One minus one. I'm trying to confirm whether this is true. 1 minus 1, 1, 0. What happens if we multiply the vector 1, 0 with this matrix? Can you help me here? What is this?
We have a 2 by 2 multiplying by 2 by 1.
Okay, but what is the answer? Is this true? Can you check if this is true? I'm not sure whether I'm going to find what I'm looking for because I don't remember this matrix. So I just want to do a double check. So is this correct?
Yes, the first one.
Here, okay, this doesn't look very right to me actually, so here we get -2. Wait a second, this cannot be like this. Maybe there is a different vector, so this is 1 minus 1, 0, 1, multiplied by 1 minus 2. So here we get, oh no, this should not be true. Then here we have 1, this is -1, -1 minus 2, we get -3. Now this is a progression, so this is not the correct matrix. Let's try this one, 1 minus 1, 1, 0. Let's multiply this with 1, 1. What do we get? This is 2 minus 1. 1 minus 1, 1, 0 times 2 minus 1. What is this? This is equal to
2 and 1.
No, is this correct? Can you check if this is true? This is equal to 1. 1 minus 2 is -1, -1. Okay. And then I'm really trying to pick up some. Okay, so 1, 0. Let's do this one. 1, 0. -1, -1. This is -2. Then here we get -2, 1. So if you notice here, I got the negative of this vector here, okay? But I need some help because I make mistakes when I multiply these. Is this correct? -2, 1. So this is -2, 1. And then we get here -2, this is 2, 3, okay, -2, 3. Can you check my calculations?
Until now, they are right.
They're good? Okay, thanks for confirming, because this is -2. Then here we have
-2, 5.
-2, 5. Then if we multiply here, no, I cannot find this matrix. I mean, if you check your notes, you should be able to find what I'm looking for, and then try to derive it again. But let's see, we get here -2. No, now we got stuck. Okay. Then we get, yeah, we got stuck because this is going to be
-2, 7.
no, this is 2 plus 5 -2, 5. Oh, we got stuck here? Wait a second.
-2, 7. If you multiply,
Okay. But still, we got stuck. -2, 7. So this -2 we will not be, but no, I made a mistake then. You see, I should use the same matrix here, 1, 0. So you don't correct me, you don't see my mistakes. So I apologize for this, but we will fix it. -2, 1. Куш по-confirmăm dacă rezultatul nu exact? Să iei să suniu găzări?
Fabio.
Flavio, Flavio.
Fabio.
Fabio, Fabio.
Po shikoj vetëm vektorin e dytë, jo matriksin.
Po putem kamera. Yes, that you so we get here. This is equal to 1. Okay. This is 2. We get here 1, 2. Okay, let's see what we get. Okay, starters. Is this correct? No, it should be wrong.
-1, 2.
-1, 2, right? This is -1, 2. Wait a second. Yeah, it's -1, 2, right? Okay. -1, 2. Let's move ahead. So what do we get here? Here we get
1, 1, do good.
this is 1, 1. Is it 1, 1? Yeah. So do you notice something? It looks like, what is the difference between this and this? So here, this is an angle of plus pi. So we have rotated this vector by pi. So we get minus this one, right? Here, we have rotated this vector plus pi. And this one is rotated plus pi again. But I'm not over yet, because I should be, okay. probably will soon be home. Now, what we're trying to reproduce again is an old problem we did in the class, but I'm trying to do this, or I was trying to remember what the correct matrix is. Where did we start from? We start from 1, 1. Oh, we came back. No, we found it, you see? We started, so okay. Let's try to see what we just did. Here, this is 1. Fabio, stay attentive. So we started with this vector x0. Okay, let's call this one x0. And we did a times x0. This is equal to x1. Okay? What is x1? x1, it is 2 minus 1. So this is 2 minus 1. So this is x1. Okay? Then, what is x2? x2 is 1 minus 2. Where is 1 minus 2? No, we have a mistake then. It should not be like this. 2 minus 1. No, this is wrong. Fabio, where
No, I just passed that phone, idiotă, pe acolo în apare.
I made a mistake. We corrected it very fast. X1 is this, right? So let's take this away. Because it looks like we are rotating it the other way around. So we get here 2 minus 1 is this, then we get 1 minus 2. So 1 minus 2 is this. Okay. So x0, x1, x2. So this is 1 minus 2 minus 1 minus 1. It's this vector here. Okay. So this is x3 minus 1 minus 1. Then we get minus 2, 1. So you see, we are rotating in this direction, right? But we get minus 2, 1. Where is minus 2, 1? It's this vector, minus 2 along the x. So we get this. This is x4. And then we get minus 1, 2. Minus 1, 2 is, apparently this is x5. And x6, what is x6? So we are drawing these vectors. It's 1, 1. So we came back here. So x0 is equal to x6. Okay? Can you see these? So this was x0, this was equal to x1. Then we do a times x1, this is equal to x2. A times x2, so let's write this one. A times x2 is equal to x3. Okay, this is x3. And when we roll these vectors like this, we can easily notice that we are rotating from here to here. How many times are we operating with the matrix? 3 times. Okay. And let me also write it like this. This is x0. x1 is equal to a times x0. x2 is equal to a squared times x0. Do you agree on this? Are we okay here? Is it clear?
Yes.
Okay, so please give a sign of confirmation. So here we started with x0, we rotated it by multiplying the matrix A, we multiplied it again, this becomes a squared times a is x0, then this is equal to a cubed times x0. Here we get a to the power 4 times x0, and this is a to the power 5 times x0, this is equal to x5, and this is equal to a to the power 6 times x0. So what is this matrix A? It looks like the matrix A, it is a rotational matrix. Okay, that's good for us. It's a rotational matrix, and what do we observe here? So A, apparently, let me write this one, and I want you to write this on some piece of paper because I always forget. This is 1 minus 1, 1, 0. So it looks like a to the power 3, what is it? What is a cubed? A cubed, it's equal to minus 1, 0, 0, minus 1. We can easily see this because this is x0. If we multiply with a cubed, we get a negative. You see this? And also, this is x1, which is a times x0. This is the negative of this other element here, okay? Which is CEN. So you can see that we can rotate by pi, but rotating by pi, this is You are multiplying by -1 all elements, right? And finally, we see that a to the power 6 is equal to what? Who can find what is a to the power 6? So this is the identity matrix. Okay? So what is the difficult part so far? Was there anything difficult here? So a to the power 6, what did it do? How many degrees did the initial vector x0 rotate when we applied a to the power 6?
It rotated 360 degrees, so it's in the same position.
That's true. So a to the power 6, this rotated the initial vector by 360 degrees. So on average, what was the angle? So this is approximately 60 degrees, right? Because 60 times 6 is 360. Are we okay?
Yes.
Yes.
But this is not exactly true, because these angles are not equal. Because we can see that these are, right, if you calculate the angles, they are slightly different. Because here, now it's a little crowded, but if I draw this one in blue, we started with this, we go here, 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 here. The angles are not the same, I agree with that. You can say, no, professor, you're wrong, of course. But now, you know eigenvalues, and you know eigenvectors, okay? So let's try to find what are the eigenvalues of this matrix A. How do we find the eigenvalues of matrix A? We do 1, 1, minus 1, 0, minus lambda, 0, 0, lambda, right? This is what we do. Then we have 1 minus lambda, 1, minus 1, 0 minus lambda, minus lambda. What do we do next? Someone can raise your hand and help me here.
We find the, sorry, let me raise a hand. We find the determinant to find the lambdas.
Yes, so this is...
So 1 minus lambda times minus lambda.
Wait a second, so, okay, so let's do this because we might, we have, well, let's do it like this. Lambda minus 1 times lambda, so this minus 1, we give it here.
Plus 1.
Plus 1, thank you, this is equal to 0. What else? Lambda squared minus lambda plus 1, this is equal to 0. What are the roots here? We should get at least 2 roots, right? We said that this is a polynomial in second order in lambda, so we should get 2 roots. What are these? We have lambda 1, lambda 2, it's equal to minus b minus 1 plus minus, minus b, no, that's 1. Minus b plus minus b quadrant. B squared minus, this is 1, minus 4ac, minus 4 divided by 2. Is this correct? Is this correct?
Yes.
Okay, if this is correct, then we have here 1 over 2 plus minus I square root of 3 over 2. Okay, so it looks like one of the lambdas is equal to, so lambda 1, it's equal to 1 over 2 plus I times square root of 3 over 2, and the other eigenvalue is lambda 2, it's 1 over 2 minus I times square root of 3 over 2. Now, I want you to look carefully. These are complex numbers, right? And you know Euler identity. You are specialists in complex numbers. So we know that e to the power I theta is equal to cosine theta plus I sine theta. This is called Euler identity. Now, I want to ask you this. Can you find what is the cosine here? Which angle has a cosine 1 over 2? Can you check this?
60 degrees.
60 degrees.
That's correct. Which sine is square root of 3 over 2?
60 degrees too.
60 degrees, that's correct. Okay, so apparently this Euler identity, we can write it like this. So it looks like lambda 1, it is e to the power I60. Okay, do you agree on this one?
Yes.
Yes.
Yes. I mean, yes, because this is cosine plus I sine. This is e to the power this, and this other one is this. Okay. So now, what we see here is that based on the principles that we learned from the complex numbers, it looks like this matrix A, which we try to derive it actually by randomly checking the numbers, what we see is that matrix A, it rotates on average any vector by 60 degrees, okay? And so we see this here, right? We argue this one. And the point is that the angle between x0 and x1 will change. How will it change? We assign here x0 as 1, 1. We started from here, right? We could have started from another vector. We could have started here. And then the subsequent angles that the vector is rotated, it will change. But after 6 multiplications, there will be 360. So based on this argument, we can say that matrix A, it rotates the vectors on average by 60 degrees. So whatever a matrix does to a vector, the same thing is done by the eigenvalue, okay? Because we can see that the eigenvalues of this matrix, this is what they are. And we know very good what happens if we multiply a complex number. So let me take this away. So we said before that if we multiply e to the power I60 with a complex number such as, which can be, let's say, 5 times e to the power 30, okay? So we are multiplying a complex number, which in this case, this complex number, this represents a vector. Why is it a vector? Because it has a magnitude of 5, and we can find it at an angle 30 degrees with respect to the x-axis. If we multiply these two together, we get 5 times e to the power 30 plus 60, right? So this eigenvalue of this matrix, which rotates any vector in the two-dimensional space by an average angle of 60 degrees, the same thing is done by the eigenvalue, okay? Now that you know the complex numbers, I really like to talk about the complex numbers because it is a little more obvious how similar, or not how similar the matrices and the complex numbers are. That's one thing. And also, you can more easily see the effect or the beautiful equivalence between what the eigenvalue does and what the matrix itself does. Do you have any question for what we did so far?
No, it's mostly clear.
Okay. We can have a short break and we can stop this session.